All right, I wrote up a solution to another homework problem. This one's from 5.2 and it's number 45. It's one of the applications problems from the section, and the problem was basically to come up with a maximum for the profit function. And the idea is you were given some basic information. You were given a cost function. And so the cost was a function of Q, which was the number of units produced, okay? So the cost to produce Q units is given by this function model. And you're also given kind of a demand equation, which is what you have to set the price at for a certain number of units produced and sold. The idea being the more units that you produce, you can afford to sell them at a lower price, basically, okay? And so what you're supposed to do is use these two given functions to maximize the profit function. And I used a kind of a capital P to change it from the price per unit here, the little p. But anyways, profit is the revenue minus the cost. Revenue is the amount of money you bring in minus the cost. And the idea is to model profit based on the number of units you produce and sell. Okay, so as a function of Q in this case. So the revenue I claim is P times Q. P is the price per unit. Q is the number of units. So if it's $5 per widget, and you make and sell 100 of them, it's $500 total, right? So it's the price times the number of units minus the cost function to produce Q units. That's C of Q, not C times Q. And so plugging in the information that's given, that's Q units times the price per unit up here, minus the cost function. Just be careful to use parentheses in here. All right. And then I simplified it just a touch. Notice that 30Q times this exponential minus 10Q times that same exponential becomes 20Q times that exponential. Minus 100 there for part of that cost function. So this is my profit function as a function of Q. And the next is to try to maximize it. Okay. So in order to maximize, what we're going to do is try to take the derivative of that profit function and then set it equal to 0 to find critical points. And so when we take the derivative, notice it's a product rule and a chain rule involved here. I just kind of jumped to the answer, but if we take a quick look at P, again, looking at this first term, it's Q times a function of Q. 20Q times a function of Q. And so basically it's the derivative of the Q times the rest, which is 20e to the minus 0.02Q. Plus the derivative of e to the minus 0.02Q times 20Q. And that's where the chain rule forced a minus 0.02 to come out as a multiplier. So we have a plus went to a minus. 20 times 0.02 is 0.4. Okay. So maybe the hard part, I should maybe shown more steps, but taking the derivative was a combination of the product rule and the chain rule. Next is looking for critical points or critical values. Now this profit, the derivative of the profit function, the marginal profit that's called sometimes, is defined everywhere. And so you only have to look at the places where the derivative is equal to 0 in order to maximize. So what I do is I look at that and I factor P prime and set the factors equal to 0. Well, this amounts to solving this equation. 0 equals 20 minus 0.4Q. When we do that, we come up with Q equals 50. Okay. And now we just have to realize that this quantity Q equals 50 is a maximum value. If you actually looked at the derivative values here on either side of 50, if you plug in a number less than 50, you get a positive value for P prime. So profit's increasing before 50 and it's decreasing after 50. Okay. And so yeah, this was really a maximizer value, maximizer quantity, 50 units. The price per unit, if I plug it back into the demand equation, this one here, the price per unit, when just plug in Q equals 50, you end up with 30e to the minus 1, which is about $11.04 a unit. And then the actual profit for producing 50 units, we just plug it back to the original profit function, by the way, not P prime, but in the original profit function, this one here. and we come up with a profit of approximately $267.88.